Dr. Singh.
Thank you, Dr. Peterman. Great introduction. Let's see. Good morning, everyone. Okay, my name is Muchar Shin. Today, I'll be talking about the development of a high-performance concrete using non-steel fiber for pre-stressed concrete cross ties. So it is always an honor to be here back to our campus and talk about some of the things that I'm doing. Before I'm going into the presentation, I would like to acknowledge all the researchers, co-PIs, and especially our undergraduate researchers. So Western New England University is located in the Springfield, Massachusetts. We call Western Mass. So we are far from the Boston area. So, but we are a small private school and we have brilliant undergraduate students. So we have to work together with undergraduate students. So we have Ivan, Krista, Brian, Daniel, Archer, and Robert. So they always come to the concrete lab, structural lab, mixing the concrete, get dirty and hands-on, and try to see how the concrete performs, and try to educate them with give the hands-on experiences, concrete with the fibers. We can make it the infrastructure better. Yep. So from the title, you can see that I'm focusing on non-steel fibers. So again, the concrete is susceptible to crack. So the way that we can minimize the cracking is adding the fibers. So it has been known to the earthquake engineering domain. When there's earthquake happens, the buildings and bridges, we added the fibers and it shows great ductilities. So in the concrete cross ties in the North America, especially we don't have the transverse strut. So some of the cracking and the splitting is a great issues. So why don't we add the fibers? But some of the researches and also the actual product is using the steel fibers. But where we are at now, Northeast, the corrosion is a huge issue. Also, I'm working for the TIDC, which is the UTC, USDOT UTC Region 1 Center. They are focusing on the durability and also durability of the infrastructures. So they are pushing the non-steel product, especially pre-stressing steels. So today, I would like to introduce my project, and also we did some of the testing, and I will show you some of the fresh concrete properties, hardened concrete properties that's regarding F''C, as well as the fracture toughness testing. And also we conducted the corrosion test as well as the impact loading test. And I will conclude my presentation with the future work and a concluding remark. So objective, we would like to develop fiber reinforced high performance concrete, which can enhance the crack and impact resistance and the durabilities. So we use the minibar, which is so-called minibar, but that's basalt fibers. So there are two types of the minibars we are using. One is longer fiber, which is 44 millimeter, and one is shorter fiber, which is 22 millimeter. So again, from the high-performance concrete domain, earthquakes and elsewhere, they already conclude that if you have the low strength or minimum strength concrete, let's use longer fibers because the bonding can be issues. But if you have the high-performance concrete or ultra high-performance concrete, it tends to use shorter fibers because the bond strength is high enough. So we would like to use whether that's the case for our concrete as well. So Dr. Riley already went over these damage types of the concrete cross ties, so I don't need to bore with you all the damage types. But again, the concrete tends to cracking, have many issues if there is some stress built up. And then we would like to minimize the cracking issues. So again, as I said before, one of the way to minimize the cracking propagation is adding the fibers. So this is one of the examples I also was involved in. This is the collaboration research with the Korea Railroad Research Institute. They actually developed ultra high performance concrete with the steel fibers. So F''C of that UHPC is 150 megapascal. So that is about 20,000 PSI concrete, but they added steel fibers. So in this UHPC with the fibers, how much dosages of the fibers we need to add to achieve certain performances? So their study concluded that 1% of a steel fiber is the optimal dosages of the volume of the concrete. So top left corner, that is the stress strain curve in tension of the concrete. That's a direct tension test. So again, when you conduct a direct tension test with the dark bone shape of the concrete with the fibers, the alignment of the fibers is well aligned or well distributed. It's not so random. So when you try to use that dark bone curve or the stress strain curve in the real structure, the orientation of fiber is not well distributed. So there is a fiber reduction factors. So what we found is that is about 0.85. So 15% reduction of what you're gonna get from the direct tension stress tension test. And then we tested at the rare seed, and then we captured various properties, mechanical properties. But what we have found is the initial cracking force is about 50 to 100 kips, so which is significant. And also after that, it has the really good post-peak behaviors. So this study shows that UHPC is great and also fiber is great, but the cost is an issue. So again, through our study, what we are hoping is the certain design criteria or the performances. We want our concrete to be economical, and also we don't want any irregular or we want to have the smooth surfaces. Again, when the crack is occur, when the steel fiber is there, if anything goes wrong, abrasion is an issue, then steel fiber can be bad. So we want to have the softer material, yet still in the gray fibers functionality. And also we would like to improve the durability of the high performance concrete. So I dropped the U ultra. We are not shooting for the 20,000 PSI concrete. Again, if you are going there, you have to get rid of all the coarse aggregate. Again, if you are using the only fine or those cement type of the powders, again, your cost is going up significantly. In order to keep our concrete economical, we have to use the coarse aggregate in some amount. So that's why we call that just high performance concrete. So design strategy is maximize the use of the coarse aggregate. So we have contacted our local parties in the Massachusetts, in the Connecticut. So we try to get their coarse aggregate. So maximum size of the coarse aggregate we are using is a 1/2 inch coarse aggregate. And then try to fix the maximum paste volume by 40%. So we, again, high performance concrete, UHPC, the shrinkage is can be the issue. So we would like to minimize shrinkage cracks. And also we would like to consider angularity of their aggregate, again, morphology of the aggregate. So we have great expert in this building, Dr. Tudmore. He is looking at the morphology effect on the ballast, but again, the angularity and also the sphericity of the aggregate can affect the concrete performance as well. So we would like to look at how we can improve the quality of the concrete by considering the angularity of the aggregate as well. So why basalt fiber or mini bars? So we, again, as I discussed before, we want to have the non-steel fibers. So we look at the outside, because I'm at the TIDC Center, we have a great relationship with these manufacturers. Reinforced tag, they now producing mini bars. Their mini bars has been used in the European countries as well, so in their product. So again, they contacted us where we have the conversation. What is the good size of the mini bars or a basalt or non-fiber we can use? So they said, oh, for your product for the concrete cross ties, how about try to use 44 millimeter and 22 millimeter? What's going to be the work the best? So we choose these 2 mini bars, and we also look at the the SEM images and try to see whether it has to be well protected due to the secondary alkali resistance. So, but when you take the SEM images, it's well coated, so we don't need to worry about the alkali resistance or the reactions later on. Also, one of the things that we worried about is the segregation of the minibar when we are mixing the concrete. They said that at the very beginning, if you are using the shear mixer, maybe minibars will not survive well. So we try to look at the specific gravity. Again, there is no segregation as it is well mixed with our mixer, shear mixer. It is working fine. But at the first, they recommended to use the not shear mixer, the regular gravitational mixer, the drums, if you will. But again, drum, if you are using drum, try to mix the high performance concrete can be an issue. So again, for the high performance concrete domain, we tend to use high power shear mixers. So again, we cannot give up, shear mixers, but because of specific gravity, how they mix with our concrete mixtures, that it is just working fine. And then the tensile strength was given to us as a spec that was about 145,000 PSI. So what we did is, first one is the fresh property, which is a setting time, as well as a flowability or workability. So when you have the fibers, surface area increases, so that might increase or reduce the flowability or the workability. So we try to see how much setting time you're gonna get, how much slump you're gonna get. So target slump was the 5 inches. So which was good. We achieved with a good workability, even adding the fibers. So we don't lose much of the setting times. According to the ASTMC 403, we did the penetration test or resistance test, try to looking at the setting times. So with the references, when we compare it, there is not much differences. But with the high performance concrete base or high performance concrete, the setting time is a little bit longer. But if you wanted to meet the time window for the releasing the pre-stressing wires, we can just steam curing. So this is all without the steam curing. So, and then we did our compressive strength test, C39, as you already familiar with the 44 millimeter wires or mini bars. As you can see, the blue line is the reference line. So we are targeting the just regular concrete 5,000 to 6,000 PSI, and the adding fibers for 44 millimeter wires. The compressive strength increased a little bit, about 7%. And then the optimal volume of the fiber turns out to be 1% or 1.1%, but that is pretty much aligned with the steel fiber research result. So we move on to the shorter fiber, 22 millimeter wire, but we have better result. So the strength increasement was the 21% or 22%, and then also volume. Optimal volume turns out to be about the 0.5 to 1%. So in this study, what we had found with the just base concrete, low-end concrete strengths, shorter fiber is just working fine with all our ingredients. So let's go with the 22 millimeter wire, as well as the 1% dosages for the high performance concrete. So we now get our baseline for the high performance concrete. The baseline of the high performance concrete, we are aiming at the 10,000 PSI at 28 days with the no steam curing. So, and then we added the, actually tested 2 fibers, although we know that we're gonna work with the 22 millimeter wide fibers. We tested 2 types, longer and shorter, and then both of them shows this similar result. So the strength increasement was not much different. So 22 millimeter wire, 44 millimeter wire, they show the similar result. And also the slump, we didn't lose much. So we are at, having about 5 inches or 4.5 inches of slump. So that what that means is we can give our mixture design to the local site. They should be able to mix it. So that's the whole one of the objective of our study. So we don't want to have special mixture design which can only mix in the special lab. Again, our workforce is majority are the undergraduate students. So sophomore to the seniors. So we seniors are training these sophomores. Our students can make this concrete in the concrete lab in the smallest private school, then I think any manufacturers or the industry can make the same type of the concrete, high-performance concrete. So there is no significant difference in the compressive strength between long and short fibers. So after that, we try to see what is the tensile performances by doing the fracture energy test. So we have the beams, we have the notch in the bottom, we have the CMOD crack mouth opening displacement gauge. So try to look at how much crack width is propagating or it gets wider while you are pushing down, we're applying forces. So as you can see, this bottom right corner, this is the force crack width relationship, and then comparison between the high-performance concrete and conventional concrete. So both of them are without the fibers. So we can see the high-performance concrete has the higher fracture energy as well. And then now we added the fibers. So you have the red line and then a little bit of a darker red line that is with the fibers added to the conventional concrete. So as you can see that the fracture energy is significantly increased, which is the GF value, Newton per meter. So it's normalized by the area of the crack surfaces. So that is 5,000 or 5,500, where CC or conventional concrete is about 250 or 229. So that is significant increase. So and also in the bottom left corner, you can see that maybe, but the orientation of the fibers. So you cannot control the orientation of the fibers. That's what you're gonna get. That's why you have after the peak, you have the so different post-peak behavior between the two samples. Again, so that orientation, as much we would like to have the well-distributed fiber orientations, but that's impractically, it is impossible. So the total energy will much vary, but now we are in the phase of the testing, the high-performance concrete with the fibers fracture energy testing. So one additional thing, where one of the objectives of this study is durability, how we can see measure the corrosion resistance of our concrete. So one of the challenges was how you can define the corrosion level with the values. So from the bottom pictures, you can see that this is intact. Another one is just cracked. So 0 to 100 is well defined, but how we can define the between? So we try to define where we are able to define the degree of the corrosion by the charge. So we are able to monitor the current throughout the time, and you just take an integration of the current that will give you the charge. So you can we are able to pinpoint where the corrosion is happening and how much charge we are putting into the system in the accelerated corrosion testing. So we are able to correlate the damage level versus how much charge we are putting into. So in the bottom pictures, you can see that again, the top one is the high-performance concrete after 48 hours exposure to the accelerated corrosion testing chamber, and then conventional concrete. So it's well cracked completely. HPC, even without the fibers, it survived well. So now, and again, we are in the phase of the testing HPC with the fibers in the corrosion chamber. So we also did the impact load test. So we developed this impact load test apparatus. We are developing 18 pounds of the mass at the designated feed. So we are able to calculate the energy, potential energy, so we can quantify it. But I prepared the 3 images. The first one is the reference with the conventional concrete. When you drop it, it's totally smashed. FRC, this is a fiber, conventional concrete with the fibers. HPC is just high-performance concrete. So after impact loading, it is able to survive, but try to energize access. I prepared the videos. That's the normal concrete. That is fiber reinforced concrete. And this is HPC. Come on. Maybe not. Or you survived. Oh, there we go. Oh, that's why that's a slow video. That's why it takes so longer. So one more thing, this is not, it's somehow related, but it's not pre-stressed concrete. But I also taught the construction materials this semester. What we did is to our students who exposed to this kind of research, they try to make use out of the fiber reinforced high-performance concrete. So what they made is this tensegrity. Some of you might be aware of this structure. It's a floating structure. Normally it's made of the steel because every part of the structure is subjected to tension. But we suggested, how about make out of the concrete? So our concrete is great in tension. How about making together? So our students made that tensegrity structure. We are able to take up to the 300 pounds and start jumping up and down. It was great. So it's not only try to do our research in the railroad domain, our students can take a great use out of it. So our students is really proud of their product. So some of the conclusions, adding about 1% basalt fiber is great in the compression and tension as well. And crack and impact resistance are significantly increased. Corrosion as well as impact loading resistance was greatly enhanced. So HPC with the basalt fiber shows a great potential in the durabilities. Future work, we will do the accelerated corrosion test with the HPC with the mini bars, and also we will do the proud test, try to see the bonded strength of the high-performance concrete with the mini bars or the fibers. So I would like to acknowledge the great support, funding support from the TIDC located at the University of Maine under the US DOT UTC Region 1 program. And also thank you for the Bosla donating some of the bars, pre-stressing wires, their support, some of the meetings we have, and also Dr. Eileen Yu, her expertise in the concrete cross ties. So I would like to have any questions if you have. Thank you. Yes.
Have you done any freeze-thaw experiments with concrete?
We would love to do that, but UF is the go-to-go. We don't have that, testing apparatus. Yes. Okay.
What effect do fibers have on modulus?
Oh, I don't think there will be a great effect on the modulus, but we haven't measured the modulus yet. We will be measuring the modulus together. So, but I don't see that there will be much differences in the elastic modulus of the concrete in the compression. And then also it might be notified by in here fracture energy test. The initial slope is almost identical between all the three testing samples. So I imagine that there will not be much of differences. Okay, thank you. I'll be around. So if you have any other questions, please grab me. Thank you.